Alright, welcome to the 6th video in this channel. And today we're going to be applying what we learned in the previous video about angular motion into our physics engine that is in Unity. So, let's get right to it. This will probably be a very short video because it's actually very simple. You see, we have Unity open right here, and I'll double click on my WMP script, which is my physics engine. I called it WMP because wave matter physics. And here we have the physics engine itself. We have all of our public variables. We have the get position function, right? These are the only two things we have right now. These are what the player or user will see eventually. And this is the function which allows us to find the position of our object. But that's only on like an XY plane, and that's with, as I said in the previous video, parabolic motion or linear motion. It doesn't account for angular motion. So what we're going to do is we're going to create a completely different function. And we're going to call it get angular position, put in those with this, and we're going to put our equation for finding the angular position in here in a completely different function. Okay, so first off, we are still going to need time, because if you remember in the previous video, we had in the function that Professor Shankar gave to us, it was r as a function of time, where r is our position vector. So we're going to have float time, just as this one right here, float time as our parameter. And we want to start with our return thing of what we're actually going to get from this. So we know that we're going to return a vector 3, and it's going to be the position vector. So I'll call it that. Oops, sorry, I wrote my code wrong. Vector 3 position is equal to vector 3 position is equal to new vector 3, and then that's our vector in there. And then we want the function itself to return the position. Okay, this is just real quick setting up everything, because right off the bat we know that we want to return a position vector. So I'm just setting up the vector 3 position, and whatever we do is going to go in here. So to set this one up, first off, we're going to need some new variables. New stuff for the player or user, rather in this case, for the user to put into the script through Unity's game engine itself. So we're going to make public int, and we're going to call it omega. Actually, I'm going to make it a float because of reasons that I will explain later. Omega is our angular velocity, right? So I'm making that. I also know that I'm going to need a radius, which is my magnitude of the position vector. So I'm going to create a public float called radius. And I'm also going to need, what else did we need in that? Nope, this is just it. Okay, so I have omega and I have my radius, which is my magnitude of this guy. So what I'm going to do now is I'm going to set everything up for the actual vector. Now, if you remember, the circular motion, the angular motion itself, was happening on an xy coordinate plane. It wasn't happening as an xt graph or something like that. We actually did label it as y and x. So in this case, I'm actually going to do an xz coordinate plane because that way it's just easier to see within the within Unity. So what I'm going to do is I'm going to create my parameters for the parameters. No, I'm going to create the x value of my position vector, right? And I'm going to set this up like so. I know that because I'm doing an xz coordinate plane, I don't have anything going on in my y. We're going to tackle how to do 3D stuff later on. And then I know that I'm also going to need a z value for my vector. So what I do is I go float z value. Remember, this has to be a float because components of a vector within Unity are always floats. So as you can see here, my y value I put in as a 0.0f, marking it as a float value rather than just an integer value. So I have an x value, I have my z value, which will not show up yet because I have these as incomplete, but here it is. Now, Control S that. We're not done. We have this, and we have this, our x and z values, and in my physics video I said x and y, but we have x and z values. If you remember back to the magic equation that Professor Shankar gave us, it said, off the top of my head, r as a function of t is equal to radius into, as a whole, I cos omega t plus j sine omega t, right? So our I and j components are our x and y components, and in this case, our x and z components. So what is happening with the I? The I is attached to the cos omega t part, correct? So what I'm going to do is I'm going to call on the cosine function that is within Unity. That's through mathf.cos. And this will take some value in radians, but we're going to think about that later. For now, we know that we're going to have cosine, mathf.cos, omega into time, which we've established as a parameter. That's great. Okay, I can end that with a semicolon. But remember, in my magic equation, I also have radius being multiplied into the entire thing. That means that if I were to have these as separate parts, because this is basically my I component, if I have radius multiplied into the entire thing, that's basically the same thing as radius into cosine omega t plus radius into sine omega t. So what I'm going to do is I'm going to multiply my radius into this entire thing, right? Then it's practically the same thing here. Now, instead of doing radius, I do mathf dot, if instead of doing sine, I do cosine, I do mathf dot sine. Sorry about that. And then I do omega into time. Okay, this is great. And I'm going to label this as my j component. Going pretty fast here, but there's not much here for me to explain. This is basically our magic equation, which was, if you remember, as I've stated before, r as a function of t is equal to r into, as a whole, I cos omega t plus j sine omega t, right? So what I've done here is I've broken them up into these two components, put them into float values, called them x and z because I'm working on that plane, and then put those into my position vector, which is being returned. Okay, this is really fast, but this should work. So if I go to my Unity engine, oh, but wait a moment, I'm being thrown up. There's an error being thrown up. That's because in Unity, the thing is you can't just put a variable beside brackets and have it as multiply. You actually do have to have a multiply. That was just a simple error on my part. And now it should all be fine. Also, I forgot to show you guys my Unity screen. There you go. Now we're all fine. So if we go to CubeBoy, who has the script on him, we'll see that, wait a moment, we don't have these new variables. Omega, radius, where did they go? This is because, if you remember, I have this script decoupled, meaning I need to actually go into my CubeBoy script and have my new variables as variables within here as well. So what I'm going to do, I'm going to make some easier to read variables. I'm going to make a public float called angular underscore velocity, because that's my omega. Public. Also, if you don't know what I mean by omega, go check out my previous video. It's video number 5 about angular motion. And in that one, we talk about the motion of a particle around a fixed point in a perfect circle. We're going to make a float called radius, because radius is pretty easy to understand. Then we're going to do phys.radius equals to radius. There we go. Unity's doing our stuff for us. Phys.angular velocity equals to not angular velocity. As a matter of fact, phys.omega will be equal to our angular velocity. There we go. And now we just have to add another script in that says that my transform.position of this object is going to be equal to phys.getAngular position, and its parameter will be time.fixed unscaled. Ooh, fixed. How to spell that right? Fixed unscaled time. You see, the reason why I have this line is because, remember, my get angular position is a completely different function. So if I just had get position, the script wouldn't be checking for get angular position. So I have to add in an angular position function as well. So transform.position is going to be phys.getPosition and angular position. So we can mix the two together to get some interesting stuff. So everything seems to be accounted for. We double check. Omega is our angular velocity over here. That's checked. Radius is our radius. Yep. We are setting them as such. Correct. Everything's spelled right. Alright. We have it being multiplied. Everything looks good math-wise. Now to run it and see what happens. So I'll just shift over to Unity right here. And now you'll see we have angular velocity and radius over in the inspector as variables that we can change. First off, I'm going to zero my initial speed, direction, acceleration, all of that, because that's my, XY plane movement stuff. And we don't want to mess around with that for now. So, how about we give it an angular velocity of 6.28, and I'll explain why. And we'll give it a radius of 10. Let's see what happens. Now, it seems to be working. It's moving in a perfect circle. But the problem is, it has sunken to the floor. And it actually kind of hit me in the face right then. But here it's sunk into the floor. This is because the position, the vector 3 position, is coming out of an origin that we call 0, 0, 0. It's the ultimate origin point. It's when all of your axes equals 0. And right now, our cube is offset on the y-axis by about 8. And so when we run the position vector is like, well then, I'm starting at 0. And I have nothing for initial position changes, so I'm just going to move to 0 and do everything from there. But we don't want that. We want to be able to offset the point at which it's turning from, right? And time to introduce something called the axis. The axis is the point that any object that is moving along this function moves around. So in my physics video, we used the origin as the axis, but here we're going to need to use something else as the axis. We need to be able to change the axis because, and the reason why this is because I want to make the solar system within Unity. Kind of. I'm going to try and get as close as possible to the solar system. Right. So, back over to Visual Studios. Let's go to our physics engine script, and let's start making some stuff. First off, we know that we're going to need an axis, right? So we're going to make a new variable, and it's going to be public because the person who's using this wants to be able to change the axis, and it's going to be a vector 3. You see, right now we have a position vector that is being returned. But you know what would be really cool? Is if we could add a vector onto the position vector, and that way it fixes everything, right? That vector is now constantly over there. Or, even better, is if we could take components of a vector and put it into the position vector. That way we don't have to do some weird vector addition, because you see, if I put in add axis over here, it would cause problems, because the axis itself would still be from the origin, and it wouldn't actually change much, except for maybe the radius. So what we do is we make a new vector 3 called axis, and how do I do this? I can't, as I just said, I can't just simply add the axis vector onto the position vector, because if I were able to draw this out, I would, but I currently cannot. But basically, if you can think of it as two arrows, both like adding together with the tip-to-tail method, both are kind of centered at the origin, though, it wouldn't work. Well, not both are centered at, you get the idea. In the end, the resultant vector wouldn't actually be offset, it would be just farther away from the axis, which would still be the origin. Anyways, it just wouldn't work. So what I need to do is I want to return a position vector that it by itself is offset. And how do I do that? Well, you do that by adding stuff or changing the float values of its components, right? So for our x-axis, we're going to, or our x value, sorry, we're going to add the x component of axis to our x value of the position vector. It's kind of weird with the wording right there, but you get the idea. Then we do the z component of the axis for our z value, and that takes care of that. And we could try this, but wait a moment, right? Remember, we have to make a new public float, or no, public vector 3 here, called axis. That's a pretty descriptive name. We don't really need to explain it much. And we're going to have phys.axis. Oh, what did I do there? Phys.axis equals axis. There we go. Control S, and this should be fine. So if I go into Unity, show you guys Unity, click on Cube Boy, we can now see that there's also an axis. First off, let's try if this actually works. As I said before, we are offset by about 8 on the y-axis. So if we set the y value of our axis variable, there we go. If I call it variable, you guys can figure it out. It's easier to tell. If we set our y value on the axis variable to be 8, which is the y component of my, you get the idea, my y position right now for the cube, it should not sink to the floor this time. So 3, 2, 1, go. Oh my, it is still doing it. This is because I forgot that we aren't actually doing the y component there. We only added the x and z component. So let me go in and fix that real quick. All I'm doing, and I won't show you guys this, but all I'm doing is just adding the y value of the axis to my 0.0f, and that should fix everything. Yeah, there we go. Okay. Nice. This works. Now let's try in real time offset our z. This is the cool thing about having a physics engine in Unity that you built yourself. You can visualize things really easily in real time. So just by clicking on z, and I can change. As you can see, it's kind of hard, what with the white background, but you can see that it's now offset from this directional light. We'll use that as our marker. We'll change it even farther. There we go. You can see it in the game view as well. We can change it on our x-axis as well. It's fun to mess around with it. Okay. Now, sorry about that. Back to this. You know how it was like really hard to see where it was? Well, I want to make it easier. So what I'm gonna do is I'm going to have a 3D object. I'm gonna have a sphere. Or actually, considering what I'm about to do, I'm going to delete this. I'm gonna create a capsule. Why not? And this sphere, actually, never mind. Sorry about the indecision right there. That was a bit of an unexpected decision I just made there. Was not pre-planned, but we're going to have a sphere. We're going to rename it to the sun. And you can see where I'm going with this. As I teased before, I'm going to have... What do you mean a game object can't be sent to an empty string? Okay, let's not worry about that. So, we have the sun, and what we're going to do is we're going to add a component, and we're going to call it... Actually, we're not going to do anything. This is going to be our axis. Okay? This is going to be our axis, and basically we're going to use this as an identifier for where we are, or what point we're rotating around. So I'm going to make this a little bigger, as you can see. And I'm going to make it much bigger. There we go. The sun is very, very, very big, in case you didn't already know that. But it is massive. I'm going to move it off of my plane. That way we don't have all of that happening. And everything we're going to be observing most of the time is probably going to be from the project panel. So what I'm going to do is I'm gonna push the game view down here so that it's not as important. There we go, just hide it. Actually, wait, I can just do this. Scene. Sorry about this. There we go. Now we can only see the project panel, and that's much easier to work with. Now, this is the sun. We're going to create. There we go. We're going to create a new material. We're going to call it sun matte, and this is the more repetitive part of this video. I'm just going to be going around coloring things. Sun matte. We're only going to make 2 planets because otherwise it would be a pain to go through each and every single one. We're going to make a sphere. Let's call it the Earth. And bring it over some. It's so far away. This is actually kind of representative of how far away the Earth is compared to the Sun, and how small it is. My God. I didn't even realize it was close. Look at that, we'd be vaporized. Anyways, we're going to have the Earth. We're going to blow it up a little bit more. Not in that sense of destruction, but rather in the sense of size. Then we're going to create a new material. Call it Earth Matte. Make it nice and blue because the Earth has a lot of water, as we all know, as I hope you all know. We're going to make yet another material, and this is going to be Venus matte, and we're going to make it red. Yeah. There we go. Then we're going to make a 3D object. Sorry about this part of the video, but Venus. It's going to be Venus, and I can just change its XY just so that it can come here. There we go. Venus. For some reason it is bigger than the Earth, but don't mind that. Here, call it Venus matte. Okay. Right, that's the boring part of the video done. Now what we're going to do is we're going to create a Venus script. Okay, and this part should go by pretty fast. We now have a Venus script. It's loading. Unity's registering it. We now make an Earth script. Okay, Earth script. Now Unity registers it, loads it. We're going to double click on both of them, and I'm going to show you what I'm going to do. Here. So we have Venus script and Earth script. Basically, all we have to do is take our Cube script, which is, remember, the game object, Control-C, all of it except for the mono behavior bit, because that would mess up some naming stuff, and then Control-V instead for both Earth script and Venus script. And what we basically did was copy our entire game object script twice onto 2 new game objects so that we could make a solar system, kind of. So, we'll return to Unity. This part should go by pretty fast. And we go to Earth and Venus, and we're going to set its axis to the position of the sun. So its x is going to be -180. I'm going to set the y to 28, and the z is 1078. So Control V, go to the Z value of the axis. Oh, sorry. Control C, go to the Z value for the axis. Control V, Z value for the axis of Venus. V, Earth, Sun. Take the X value for the Sun. Control C, put it into the X value for the axis of Earth and Venus. V, take Y value for the Sun, final one. Earth, Y value goes in. Venus, Y value goes in. Control S everything to make sure it's all fine. Double check. And now we set some angular velocities. Right, this is going to go pretty fast because of something that I'm going to explain in a sec. But we're going to set the angular velocity of the Earth to 8. And we'll set the angular velocity of Venus to 13. This is because I googled this. This is because the speeds of the ratio of their speeds to one another is about 8 to 13. So Earth to Venus, 8 to 13. And we're going to set the radius of the Earth farther away than Venus. So radius is 15 for Earth and 10 for Venus. That way we do get the ordering right. And we'll run it and see what happens. Right, it's going to show me the game view. Yes, as you can see, these seem to be spinning, but because they're blown up so big, I have to change their values, the values of the radius a little bit more. So radii a little bit more, however you want to say. Radius of 100 with a radius of 150. This might be too big. If I go to scene, and there we go. Now, as I said, these are moving really fast, and we'll find out why in just a sec if I move into here and check my physics engine script. So right here we have mathf.cosine omega time and then mathf.sine omega time. The thing with this is that Unity's mathf, or rather mathf.cos and sine and tan and all of those that include angles, they all use radians. So if I put in a value for omega as 20, it's not actually moving by 20 degrees per second. It's moving by 20 radians per second. And if you remember that 2 pi radians is equal to 360 degrees, and 2 pi is about 6.28, meaning that I'm moving at around about 20 divided by 6 is close to 3 circles per second. Yeah, that's really fast. So the way I fix this is by adding in another set of brackets here. Then, after I multiply omega into time, what I do is I do mathf.pi. This calls on the pi, the value itself, and divided by 180. Basically, this is the conversion for radians to degrees, and this way we can actually think of it, visualize it easier. It's much easier to think of it in degrees per second rather than radians per second. Now, if you're going to have an object that's moving really fast, you could go into this code and hardcode out the mathf.pi, but for now we're going to be doing it in degrees. So I set up the same thing here, mathf.pi over 180. Control S to save. And if you actually if you remember, over here we have the same thing. We have that conversion of initial speed direction into mathf.pi so that we can put in a direction in degrees rather than radians. It makes life easier for us. So we go back to Unity and it compiles. I'll show you guys that right here. And now when we hit play, it should run much slower. There we go. Much, much slower. Too slow, actually. So what I'm going to do is I'm going to up the speed even more. I'm going to make it 10 times faster. This might just negate the steps that I took to make it slower, but let's see what happens. And I was able to explain the radians thing anyways. So there we go. That feels much better. It's not as, you know, pain inflicting to look at because it's not zooming all around the circle, but at the same time it's moving at a nice space so that you don't have to watch it creep along. And basically what we've done here is we've made a mini solar system. Kind of. We don't have Mercury and we don't have all of the other cool planets like Saturn with all of its rings, or Jupiter with its 4 big moons, or the moon itself circling around Earth. But we have our solar system. And yeah, that's basically one thing that you can do with angular velocity in Unity. Another thing you could do with angular velocity, technically speaking, you could make the object itself spin, so by affecting its rotation like that. But that would require me to make another script for rotational velocity or something like that. So that was a pretty fast-paced video. That's because if you look at the time for this video, it's actually really high. Anyways, so that's about it for this video. In another video, we're going to do 3D angular motion, but yeah. Nice.